Hello. Okay, so welcome to EE 151, Signals and Systems 1. And as I said in the email, we will basically start with some mathematical preliminaries that will be useful for us in the remaining part of the course. The course will be hopefully different from undergraduate Signals and Systems courses, in the sense that we will pay more attention to mathematical detail. So to give you an example, when we will study the Fourier series, and Fourier analysis is a big part of this course. So for a periodic function, we will have x of t written as a sum of those complex exponentials, or the trigonometric functions, the sines and cosines. And we will ask ourselves, so basically this is an infinite summation, k is an integer, and we will ask ourselves, what is the meaning of this equality here? Okay, so this equality is not high school equality. This equality basically does not mean that for every real number t, that if you put t here on the left-hand side, and then you put t there and evaluate the summation, then you get the same number. Okay, so what is actually the meaning of the equality that we have here? Is it point-wise equality? And sometimes we have point-wise equality. We have equality for all real value t. Sometimes we don't have this. So what is the interpretation of this equality here? And then there is a more fundamental question: why actually we can use those exponentials, which by Euler's identity are sines and cosines? Why can we use sines and cosines to represent signals that have a finite energy on their period? Okay, so why is this even feasible? It's like we are saying that those sines and cosines are a basis. Okay, so we will try to, for example, prove that they are actually complete. You can use them to represent periodic signals with finite energy, and so on and so forth. So basically, we will try to pay attention. So typically in undergraduate, studies, you will just take the Fourier series and you get functions, periodic functions, and you basically compute the coefficients. Sometimes you study the properties and so on, but we will try to go a bit deeper than this. So this course is mathematical in nature, and you need to take the course. You need to be basically to be fond of these things. Okay, if you are not, then this course definitely is not for you. Okay, and there is nothing wrong about this. Okay, so but you should have this passion for understanding mathematical subtleties. Otherwise, this course will not be suitable for you. Okay, so signal processing and digital signal processing basically relies on a certain mathematical structure, called a separable Hilbert space. And basically, things, when we do integrals and so on, it should be the Lebesgue integral. Okay, so Lebesgue integration. This is actually the way that we should do integration when we do things like probability or signals and systems. But I mean, this will be far-fetched for us. And what we will do, in this course, is that we will continue to use the Riemann integration, the stuff that you already know, maybe from high school. But we will need one additional piece of information called sets of measure zero. Okay, so we will try basically in this lecture. Hopefully by the end of this lecture, we will know this business of sets of measure zero, if you do not already know about them. Okay, so let's start with infinite sets. Okay, so sets containing an infinite number of elements, and those sets basically they come up with different flavors, different cardinalities, as we will see. Okay, so let's tell the story. We will need to remind ourselves of what a bijection is. Okay, so functions, if you have a domain and codomain, and you define a map or a function, then the function may be surjective, injective, bijective, or it can be neither surjective nor injective. Okay, so what are these things? A function g is basically surjective. Okay, so here we have a domain x and a codomain y. These are two sets, and we define a function from x to y. So we say that the function is surjective if each element in y is associated with at least one element in x. So every element in y is hit by the mapping. Okay, no element in y is left alone. Okay, each element should be used in the mapping. Okay, so this will be a surjective function. Okay, an injective function, each element in y is associated with at most one element in x. Okay, so for example, a surjective function, you can have, each element in y is associated with, at least one element in x, and you can actually choose to take all your elements in x and associate them with the exact element in y. You can do this, for example, if you have a constant function. Okay, an injective function, on the other hand, basically, you don't bother about using all the elements in the codomain. You rather insist that each element in y is associated with at most one element in x. Okay? Your function is bijective, which is a one-to-one correspondence if it is both surjective and injective. Okay, so let's give examples. Okay, so here is a map between x and y, a function defined on x. So x is the domain, y is the codomain. So what do you think about this function? Okay, now each element in y is used. Okay, each element in y is used. No element in y is left without being, the map of some element in x. So this is a surjective function, but it is not injective. Why? Look at this element here. This element is associated with two elements in x, 3 and 4. And for a function to be injective, each element in y should be associated with at most one element in x. So this is an example of a function that is surjective but not injective. Let's look here. Now, each element in y is basically associated with at most one element in x. D is associated with one element in x, same for B, same for A, and C is associated with 0 elements in x. So this function is injective, but it is not surjective because C is basically left alone. It is not associated with any element in x. So it is injective, but it is not surjective. A function, this guy here, basically this is an example of a function that is both injective and surjective, and so it means that each element in y is associated with exactly one element in x. So that's a bijective map or a bijective function. And there are so many functions that are neither surjective nor injective. So this function that you find here, it is not surjective. Why? Because A is not associated with any element in x. And it is not injective. Why? Because C is associated with two elements in x, 3 and 4. So it is not injective and it is not surjective. There are other examples. So this function here, x cubed minus x. So this function is surjective. Actually, basically all real values of y are attained by this function, but it is not injective. It is not injective because there are values of y. For example, if you take this value here, it is associated with 3 different values of x. Okay. This function, on the other hand, is injective. Each value of y is associated with basically one value in x, but y if y is 0 or y is negative. So if y is non-positive, then simply there is, these functions are not hit by the map. Okay, I didn't got this, so let me open. Okay, I couldn't see the question. So yeah, I don't know why. So it should be somewhere. I don't know. Okay, sorry for this. I missed the question. Okay, so this one. Yeah.
I'm sorry, to see the question of my colleague, you go to the chats and you have the everyone like in the top, right? So click on the arrow that says everyone. Yeah, and then you will see the private chat. Yeah, you see. No, it's Mr. Hassan. Yeah, this is the private chat that he sent you. The third one.
Okay, cool. Everyone. Then there is everyone here. I click this one.
No, don't click on it.
Yeah. Can a surjective function have elements in X? Well, yeah. So, good question. No, this is a very good question because it reminds us of the definition of a function. When you define a function on a domain, okay, you need to basically make a map for each single element in X. So you cannot basically define a function on a domain and leave one element in X without saying that g of X is equal to something. Okay, so this is something inherent in the definition of the function itself. Okay, so basically you need to define. So if I define a function, I say that g, the domain is R, then basically I need to provide g of X for every real number X. Okay, I cannot leave any X without basically assigning a value to g of X. Okay, so bijective, this is an example of a bijective function. Basically each element in Y is associated with exactly one element in X, and this is a function that is neither, it is not surjective because basically where are the function the values of y can never, here this is a function x squared, the values of y can never be negative. Okay, so if you consider your codomain to be R, then you do not hit the negative values. Okay, and hence this function is not surjective, and it is not injective because, right, if you take a value of y here, basically it is associated with two values of x. Okay, so if you take 4 is associated with 2 is mapped to 4, and -2 is also mapped to 4. So those functions basically, so this is an example of a function that is non-surjective and non-injective. Okay, so now we will use the idea of bijective functions. Okay, and this is the idea that we use to compare between sets. Specifically here, our interest will be infinite sets. So we say that two sets, okay, they have the same number of elements. They are equicardinal, and some people use the term equinumerous. If basically you can establish a bijective function between them. So you have we have two sets. Okay, if there is a bijective function between these two sets, then the two sets have the same number of elements. They are equicardinal. Okay, so let's, for example, show that this set here, this is an interval on the real axis. So this is the interval from A to B. So A is smaller than B. And we can have a bijective function between this guy and the full real axis, the set of real numbers. Okay, and what is this map, or what is this bijective function? It is this function here. Okay, so we can define g of x to be the tangent, the tan of pi over p minus a, and then you have x minus p plus a over 2. Now, what basically does this function look like? So here is the point, so this is basically this is the midpoint, okay? This is the midpoint. At the midpoint, when x is a plus p over 2, then basically g of x is equal to 0. So g of a plus p over 2, this is equal to 0. Now, if basically x is above a plus p over 2, then you get a positive values. If it's below a plus p over 2, you get negative values. And those values increase dramatically as x approaches b from the left. And it goes to negative infinity as x approaches a from the right, okay? So basically this function that you have here, okay, is a bijective function, okay? It is a bijective function. You know, each element in basically y, which here is basically the set of real numbers, is associated with exactly one element in x, and x is a number living between a and b. So because you have this bijective function between the open interval ab and the set of real numbers, then according to our criterion, basically these two sets, they have the same number of elements, okay? So these two sets are equicardinal, and we will refer here to basically the cardinality of the set or the number of elements in the set using basically those two vertical arrows. Some people use basically this symbol here, but we will typically use this. Okay, so the cardinality of the real numbers is equal to the cardinality of basically the open interval from a to b, and you know this is a sort of, you know, it's not a so intuitive result. In fact, if you really think about this, you will find that it is somehow disturbing, because we know that AB is a proper subset of the real numbers. So this is the real axis here. It goes from minus infinity to infinity, and then here is A and here is B, and that's the open set AB, okay? So it is part of the real axis. It is part of the set of the real numbers. And in fact, you know, this set, you know, this interval can be tiny. So for example, B can be equal to A plus 10 to the minus 100 or something like this. Yet, regardless, you can always construct a bijective function between the open interval AB and the whole real axis. Okay, so yes, they contain the same number of points. Very surprising result, right? But this is the world of infinities. In the world of infinity, basically, or infinities, because we'll see that there are many of them. Shortly, we'll see that there are many of them. In this world, a part can be put into one-to-one correspondence with the whole. Okay, a not so intuitive idea, but it is there. Okay, and we will see, you know, more examples in this lecture. So the idea is, again, how to compare the number, you know, to the cardinalities of different sets. Okay, so the idea, which basically originated with Cantor, the mathematician Cantor, is that, you know, you have two sets, x and y. If you can find a bijective function between the two sets, that's it. They are equicardinal. They have the same number of elements, and this is what will allow us to do comparisons between infinite sets. Okay, so let's go now to the power set. Okay, and so basically here we will prove like there is an infinite number of infinities, something like this. Okay, so the power set of a set is always more numerous. It has always more elements than the set itself. Okay, in other words, you can never establish a bijective function between x and the power set of x. Okay, so what is the power set? The power set is simply, you know, the set that contains all subsets of a certain set. Okay, so here, if x is a set and it has the three elements a, b, c, then its power set will be a set containing 8 elements. So generally, if you have a finite set with n elements, then its power set has 2 to the power n elements, and those elements include the empty set phi and the set itself, and then basically all other possible subsets. Okay, and basically it is an axiom in set theory that the power set of a set is itself a set. So it is legitimate and valid to basically deal with the power set as a set itself. Okay. Now for finite sets, it is clear that the power set is, it has many more elements than the set itself. It's just the relation I mentioned. If you have a finite set with n elements, the number of subsets is 2 to the power n. Okay, so if you have 3 elements, you have basically 16 subsets. If you have 8 subsets, sorry. If you have 4 elements, you have 16 subsets, and so on. And that 2 to the power n, it grows exponentially. Okay. But what about if we talk about infinite sets? Okay, so we in the previous slide basically we got this idea that infinities can be tricky. So you can have a set that is a proper subset of another set, okay, and yet you can establish a bijective function between them. Okay, so to say that you can never establish a bijection between a set and its power set, we need a proof. Okay, it cannot be something that is you say, oh, it's very intuitive. Okay, well, we have seen the previous slide, and you can have a tiny interval on the real axis that can be put into a 1-to-1 correspondence with the full real axis. Okay, so we should not just trust our intuition. We should basically try to prove that the power set, okay, so the power set is its cardinality is strictly larger than the cardinality of the set itself. Okay, so how will we prove this? We will do a proof by contradiction. Okay, we will do a proof by contradiction, and I think in homework 1 I think maybe in 2 places you will use a proof by contradiction. Okay, so it is a nice idea, and I'm sure that you already used it in your previous lives. So in a proof by contradiction, what we will do is that we will basically challenge what we are trying to prove, and we will assume that actually there is a bijective function between a set and its power set. Okay, so let's go through the details. So we'll assume that we have G, it's a function between x and the power set of x, and we will assume that it is an injective function. So it is injective. Now you may ask why is this? How are we guaranteed to find an injection between x and the power set of x? Well, this is guaranteed because basically the power set of x includes all the singletons, all the subsets that contain just one element. And so you can simply take each element in X and associate it with the singleton subset. Okay, so this is guaranteed. This is doable. To have an injection between X and the power set of X. But we will take this a step further, and we will assume that G is not just injective, it is also surjective. And if it is injective and surjective, then it is bijective. Okay, so this is basically an assumption. And as in proofs by contradiction, what we will try to do is that we will show that under this assumption, basically we reach nonsense. Okay, and so this will indicate to us that our assumption is wrong, and we cannot have a bijection between a set and its power set. Okay, so our initial point is that we will assume that I can take a set X and have a bijection between the set X and basically the power set. Okay. So here is how we can obtain a contradiction. Okay, so we will define a set which is called psi, and psi is basically defined as such. It is a subset of big X. So we sweep through all elements in big X, and set psi contains all elements in big X that satisfy this condition. And so what is this condition? The condition is that X does not belong to G of X. So remember that basically we have G, it's a map between X and the power set of X. So this is for illustration. So let's assume that function G, it will take A to B, it will take B to A and C, and it will take C to B and C. So this is an example of a function defined from X and B. Again, things here are basically sort of trivial because, of course, I cannot illustrate things except using a finite set. And for finite sets, it's clear, you know, that again, if a set has n elements, the power set has 2 to the power n elements, and you can never establish a bijection. But the proof basically is to serve our purposes for infinite sets. So this is just an illustration because it's sort of a trivial thing for finite sets, but this is nice to understand exactly what set psi is. So set psi is the form. We will go through each element in big X. So let's start with A. Okay, so take A. Now A is mapped to this subset, which contains B. So A definitely is not in this subset B. So A is an psi. Okay, so A is there with us. Okay, why? Because A does not belong to G of A. G of A is the subset that contains the element B. So A is with us. What about B? B is mapped to the subset A comma C. Well, B is not there. Okay, so it is with us. Okay, what about C? It is mapped to BC. No, it is there. So C belongs to BC, and what this thing here is G of C. Okay, so no, C does not belong to psi. Okay, so psi is, in our case here, it has 2 elements, which is A and B. So generally, for the general proof, again, it's as if we sweep through all elements in X, and each element is mapped to some element in the power set. And what are the elements of the power set? The subsets of X. So we examine, is X in G of X? If it is there, then it is not an element of psi. If it is not in G of X, then we have it in psi. Okay? And of course, this is a subset of X. Why it's a subset of X? Well, we construct psi by basically going through the elements of set X. So we end up with something that is a subset of X. Well, if psi is a subset of X, then it must be living here. It must be living here in the power set of X, because the power set of definition, it contains all possible subsets of big X. Okay, so psi is in the power set of X here. Okay, remember, we assume that our function is bijective, and if it is bijective, it is injective and surjective. And what does it mean that it is surjective? It is surjective, it means that there exists, there is at least one element in big X, let's call it small z, such that G of Z is equal to psi. Okay, so under our assumption, which is that G is bijective, and so it is both injective and surjective, it means that there is some element in the domain that is mapped to psi. So let's say that this element is Z. Okay. Now, the question is, what is that in psi? So, is that in this set? Okay, so let's try to answer this question. If Z is in psi, okay, then it is in G of Z, because basically G of Z is equal to psi. Again, what is this relation that we have here? Psi is a subset of X that we have constructed. Okay, psi is an element of the power set of X, which is the codomain of G. Because G is surjective, then there must be a Z such that G of Z is equal to psi. So basically psi and G of Z, they are the same thing. So if Z is in psi, then Z belongs to G, then Z belongs to G of Z, which is basically ipsi. But remember, what is ipsi? Ipsi is basically the collection of the elements in X that are not basically in the subsets to which they are mapped. So basically, if Z belongs to G of Z, you should not include it in ipsi. So by definition of by the way in which we have constructed psi, Z should not be there because it is in G of Z. So see this logical statement, does it make sense? So we start, if Z is in ipsi, then actually it does not belong to ipsi. So maybe actually Z is not in ipsi. So if Z is not in ipsi, okay, then it is not in G of Z, again, because ipsi is G of Z, basically by virtue of our assumption that G is surjective, and so there is an element Z in X such that G of Z is equal to ipsi, okay? So G is not in G of Z. But if Z is not does not belong to G of Z, then it must be included in ipsi. Okay, so if we start saying that Z is not in ipsi, then we reach the conclusion that it is in ipsi, and if we start with that it is in ipsi, then we reach the conclusion that it is not in ipsi. That's nonsense. And the nonsense means that we did something that is wrong. And the wrong thing is basically this assumption that we have that basically G is surjective. We can have an injection between X and the power set of X, but to take it further and say that this injection can be a surjection, you know, and so the overall function is bijective, this is nonsense. It will lead to contradiction, and so we should basically reject this assumption, and this means that, you know, we cannot have a function that is surjective, and hence it cannot be bijective. Regardless of whether X is a finite set or an infinite set, it is always the case that the power set will have more elements than X itself. Okay. So this is basically the conclusion, which means that, you know, if X has a certain cardinality, then the power set of X has a strictly larger cardinality. But as I said earlier, by the axioms of set theory, basically the power set itself is a set. And so you can find the power set of the power set, right? So you can find the power set of any set. The power set itself is a set, and so you can write something like this: the power set of the power set, and the power set of the power set of the power set. And basically we have all those inequalities. The power set of X has strictly more elements than X, and the power set of the power set has strictly more elements than the power set, and so on and so forth. So we have an infinite number of infinities, okay? So infinity, you know, it's not, you know, that infinite sets, they do not come in one size, okay? There is a hierarchy, okay, of infinite sizes. So the smallest infinite set, basically, you know, if I give examples, natural numbers, integers, rational numbers, algebraic numbers, and so on, and those have like the smallest, quote unquote, the smallest infinity, which is Aleph Naught, okay? And basically, you know, all those are you know, we say that, you know, the cardinality of the natural numbers is the same as the cardinality of the integers, is the same as the cardinality of the rational numbers, is the same as the cardinality of the Cartesian product of the natural numbers with themselves. Okay, so basically this is N2. Okay, so these are the ordered pairs that contain two natural numbers. All these all these, they have the same cardinality, which is Aleph Naught. And now, I mean, we say that they have the same cardinality because we can establish bijections between each pair. Okay, so you can take any two of those guys and find the bijection. And according to our, criterion for basically comparing sets, that's it. If you can establish a bijection, then the two sets are equicardinal. They have the same cardinality. Okay. So, and I think, shortly we will investigate, basically how basically something like this can have the same cardinality as the natural numbers themselves. Okay. Now, the power set of any of these sets has a strictly larger cardinality. Okay, so basically you can show. I will just mention this without proof that the set of the real numbers, it is sort of the power set of the natural numbers. You can say something like this, okay, without going into details. And so basically the real numbers, or the set of real numbers, it is strictly larger than the set of natural numbers. It has a cardinality that we denote by small c, and small c basically it refers to continuum, which is a fancy word basically for the real numbers. They are called the continuum, and c is, sometimes we write c as 2 to the power Aleph Naught, and the reason for this notation here is basically it's like sort of a generalization of the idea that the power set for finite sets, if a finite set has m elements, then the power set has 2 to the power m elements. And by our previous proof, 2 to the Aleph Naught is strictly greater than Aleph Naught, and 2 to the Aleph Naught is equal to c. Okay, so what are sets with cardinality c? The set of real numbers, complex numbers, irrational numbers, R to the n, the n-dimensional real valued Euclidean space. All these, they have the same cardinality, which is c, again, because we can have bijections between any pair of these sets. Okay, so if a set has a cardinality Aleph Naught, okay, we say that it is countably infinite. And if a set has a cardinality that is strictly larger than Aleph Naught, for example, if the cardinality is c, then we say that the set is uncountably infinite. Okay, so basically for infinite sets, again, there are many, an infinite number of infinite sets, in fact, okay, because again of this trick of obtaining the power set of the power set. But for applications like probability and signals and systems, we are typically interested in this classification. The infinite sets that have cardinality Aleph Naught, and so those are called countably infinite, and those with cardinality strictly larger than Aleph Naught, like the set of real numbers and so on. Now, basically those, something like Aleph Naught and C, those are called the cardinal numbers. Okay, and there is a cardinal number called Aleph1, which is basically the next cardinal number, so it is the cardinal number above Aleph Naught. Okay, it is just the cardinal number. So again, the smallest infinity is Aleph Naught. So this is the next guy, Aleph1. Okay, and it is an open problem in mathematics whether c is equal to n1. So this is an open problem. Okay, this is an open problem. It's called the continuum hypothesis. Okay, and no solution till now. Basically, is c equal to Aleph1, or basically there are sets with a cardinality that is strictly larger than the cardinality of the natural numbers, but strictly less than the cardinality of the real numbers. Okay, so this is an open problem. It's not, this problem is not of any interest to us here, we basically will deal with Aleph, Naught, and C, and we will not care whether C is really the next cardinal number, the next infinity. So it is the cardinal number, for infinite sets just above Aleph, Naught, or there is something between Aleph, Naught, and C. I mean, this will not be of interest to us, but it's an open problem in math. Okay. So let's establish a bijection, okay, so between the set of non-negative integers, okay, so this is sort of a cool problem. Okay, so this is the set of non-negative integers, 0, 1, 2, 3, 4, 5, 6, and so on and so forth. And then we have basically the ordered pairs of non-negative integers, okay? So this is the grid or lattice that looks like this, okay? And so we have here 0, 0, we have 1, 0, we have 0, 1, we have this is 1, 1, and so on. So basically, we are trying to see whether these two sets, okay, so this is the set of non-negative integers. I will denote it by this, okay, so this is z greater than or equal to 0, and this is z greater than or equal to 0, and then z greater than or equal. So here we have the ordered pairs containing two non-negative integers. So you may think that no way we can have a bijection between these two things. Okay, it looks like, very far-fetched, but in fact, we will establish a bijection. You should basically get used to this weird idea that we can have a one-to-one correspondence between the part and the whole. Okay, so let's see an example of this bijection, and what we will do is this. If you have an ordered pair, so from here, if you have x and y, we will assign to it the following non-negative integer. So we will take x plus half x plus y times x plus y plus 1. Okay, so if I give you and x and y, you can easily get s. You just plug in the numbers, okay? And don't worry about this. You will get an integer, right? Because x plus y and x plus y plus 1, they are two consecutive integers. And so if one of them is odd, the other is even. And so one of those guys is divisible by 2. And so, there is no problem. Basically, this half x plus y times x plus y plus 1 is guaranteed to be an integer. And then you will add x, and so you will get an integer, and you will get s. So if I give you x comma y, if I give you a point here on this grid or lattice, you can easily find the corresponding point there. But we are talking about a bijection. So bijection means the following. If I give you an s, you should be able to know exactly what x and y give rise to this s. There should be basically a unique ordered pair x comma y that is associated with a certain s value. Okay, so now here is the challenge is, now knowing s, can you get x and y? Because if you have x and y, you get an s, and if for every s you can get a unique x comma y, that's a bijection. That means that there is basically each element in, basically on this grid, on this one-dimensional grid, can be basically associated with exactly one element on this two-dimensional grid. Okay, so how can we do this? So if you think of this as an equation, we know s now, and we want to obtain x and y. Now, if x and y are real numbers, then, of course, you will say, oh, we have an infinite number of solutions, because it's like we have one equation in two unknowns or something like this. But x and y are not real numbers. X and y are basically non-negative integers. and we will see now that actually there is exactly one solution. So we don't have the case of no solutions, we don't have the case of two or more solutions, we are basically in the situation of one unique solution. Okay, so how can we do this? Okay, let's assume that m is equal to x plus 1. Okay, so remember x plus y is, it appears here, so s is x plus half m plus 1, and m is x plus y. Okay, for a given m, if I tell you the sum of x and y, okay, what are the possible values of s? Now, if x plus y is equal to m, then basically it may be the case that x is 0 and y is m, or x is 1 and y is m minus 1, or x is 2 and y is m minus 2, all the way to x being m and y being 0, right? So basically we have one possible values, from x being 0 and y equal to m, and vice versa. The other way around, in which x is m and y equal to 0. Okay, so for a given m, right, so you have an x here. So for a given m, x may be 0 and y equal to m, and in that case, s will be half m times m plus 1, or if basically x is equal to m, then s will be equal to m plus half m plus 1, which can be put as this quantity here, half m plus 1 times m plus 2 minus 1. Okay, so we can write down the following inequality. So given m, for a certain value of m, again, if you fix m, which is the sum of x and y, then basically x can be equal to 0 and y equal m, and this will give you the least value for s, which is this guy here. And then the highest value is this quantity here. Okay, so rather I will write this quantity plus 1. So I will just add a 1 to this quantity, and rather than using a less than or equal to inequality, I will have a strictly less than. Okay, so s is a non-negative integer. It is greater than or equal to half m plus 1. We have equality here if x is equal to 0, and basically s is all the way up to the integer below this guy. Okay, and this is what we get when x is equal to m. Okay, and if you run the numbers, so if you put m equal to 0, so if m is equal to 0, then x is 0 and y is 0, and there is no other possibility. And in that case, s is equal to 0, right? It is strictly, it is strictly less than 1, and it is greater than or equal to 0, so s is equal to 0. Okay, so from here, s is equal to 0. Now, if you promote m and make it equal to 1, then actually there are two possibilities. X is 0 and y is 1, or x is 1 and y is 0. And in that case, s will be greater than or equal to 1, but strictly less than s. So here, s is equal to 1 or 2. Now, if m is 2, you'll find that s can be 3 or 4 or 5. And if m is 4, you'll find that s can be basically 6 or 7 or 8 or 9 or 10 or 11 or 12 or 13 or 14, and so on and so forth. Okay? Till now, I didn't answer the question. I mean, the question is this. I mean, don't forget it. Given s, what is the ordered pair x, y? And we should get a single solution, a single ordered pair that basically is associated with a certain value of s. Okay, so how can we do this? Take s minus x, so s is x plus half m plus 1, move x to the other side, okay, and then write down a quadratic equation in m. Write down a quadratic equation in m, and basically this quadratic equation, it has two solutions. Okay, so I just use the formula for the roots of a quadratic polynomial, a polynomial of degree 2. okay? And basically, we are talking about non-negative integers. And since we are talking about non-negative integers, so this is what we do not like this non-negative integers. So we will reject the minus sign. We will not take in the negative solution. We just have the non-negative solution. And this is not useful, right? So basically, if you use the formula for the roots of a quadratic polynomial, you get something like this. And it is not useful because, you know S only. We know S only. We don't know X and Y. We want to obtain X and Y, right? So this is an expression that relates M, which is X plus Y, and S and X. So it is not useful because we don't know X. We just know S, right? So what we will do is we say, okay, so we have a minus sign here, minus X. So this thing here, which is M, is upper bounded, okay? And so we will remove this minus 8X from this, from the basically the term under the square root. And so this is less than or equal to square root 1 plus 8S minus 1 over 2. Now, what is the benefit of this guy here? This guy is computable given S. I mean, give me an S. I can plug it in and I can give you a number. But what is the problem? The problem is that this is not M. We know that M is less than or equal to this guy. But the formula for M is this one. It is not this one. Okay? It is not this. It is this one if X is equal to 0. And we don't know, right? Because, you get an S. We are solving for X and Y. We don't know yet that X is equal to 0. But this quantity is interesting. Again, it is interesting because it is something you can evaluate given S. It does not need any sort of magical knowledge about X or Y. You just know S and you can compute this quantity. Okay? So M, of course, is an integer. Specifically, it is a non-negative integer, and it is upper bounded by this quantity, which I will denote by gamma. Okay. So this may not look satisfactory, and it seems that now we are not actually solving because of using an inequality here, but in fact we have the solution now. Let's see why. So let's go back here. Okay, so this is the inequality for S, okay, and S, basically, it goes from here to there. Remember how we obtained this inequality? We said that S is equal to X plus half M plus 1, and we said that given M, X can be 0 and Y equal M, so this is basically the lower bound, and the upper bound is obtained if you put X equal to M. Okay, and then what I did is that rather than using the, so you get basically half M plus 1, M plus 2 minus 1. So rather than writing it with less than or equal to sign, I write a less than sign and I just add 1 to get this one. Okay, so what we will try to do now is that we will try to understand this gamma here. Okay, if it's, what are the bounds on gamma? What is the range of values? So gamma is a square root 1 plus 8S minus 1 over 2. So we will multiply by 8. We will add a 1. We will take the square root, and we can do so here without any problem because everything here is non-negative, so there are no worries. So we can take the square root. We can subtract 1 and then divide by 2. And we will reach a very nice inequality. We will reach the inequality that gamma, this thing here, so don't forget gamma is the square root 1 of 8S minus 1 over 2, something that, again, we can compute if we know what S is. Gamma is greater than or equal to M and is less than M plus 1. So basically, we can rewrite these two inequalities. So gamma is greater than or equal to M. So here it is. And gamma is less than M plus 1. So this means that M is greater than gamma minus 1. So you just move the plus 1 to the other side. So this is the second part, which is here. M is greater than gamma minus 1. So this is very nice, because now we know that, so gamma is something that we can compute if we know S. Now you compute gamma, it is not necessarily an integer. However, we know that m, which is the sum of x plus y, m is less than or equal to gamma, okay, and this we know from basically the solution to the quadratic polynomial. Now we know also that m is strictly greater than gamma minus 1. Okay, so this is the real axis. Okay, I give you some number gamma. Okay, I give you some number gamma. Here it is gamma, and here it is gamma minus 1. And m is basically an integer, in our case a non-negative integer, that lives between gamma minus 1 and gamma. How many integers do we have between a real number gamma and the real number minus 1? It is just one integer. And this integer actually is what we call the floor of gamma. Typically it's denoted like this. So if gamma is an integer, then we have the inequality that m is less than or equal to gamma and is strictly greater than the integer gamma minus 1. So if gamma is an integer, m is exactly equal to gamma itself. Now if m is not an integer, okay, so let's say, if gamma is not an integer, let's assume that gamma is equal to, let's say, 31.8, okay, so this will be 30.8, and so the integer that is between these two guys is 31. It is the floor of 31 minus 8, okay, so the floor of a real number, you simply remove the fractional part, okay. So m is equal to the floor of gamma, and gamma is something that you can compute knowing S. So this is great. Knowing S, we can compute gamma, we can take the floor, so this will be m. Remember that S is equal to x plus half m plus 1. So if we compute m, then we can compute x, because x will be s minus half m plus 1. And once we know x, we can obtain y, because y plus x is equal to m. So this means that y is equal to m minus x. So from S, we obtain a unique ordered pair x, comma, y. You know x, if I give you a pair x, comma, y, there is exactly one s that is associated with it. Give you x, comma, y, you use basically the expression x plus half x plus y, x plus y plus 1 to compute s. And if you know s, you can basically compute gamma, take the floor, compute m. From m and s, you can obtain x, and from x, m minus x will give you y. It's one-to-one correspondence between basically this grid here, this one-dimensional grid, and the two-dimensional grid of non-negative integers. Okay, so these two sets, they both have the same cardinality, which F note. Okay. And in homework 1, there will be one problem in which you will basically find a bijection, or you study a bijection between this set and the Cartesian product, like this. So now we will basically talk about the set and the triples. So this will be x, comma, y, comma, z. Okay, the idea is similar to what we have here, and I don't think it is very difficult. You will be able to understand that actually the trick that I used here can be extended to any dimensionality. Okay, so here we have a two-dimensional. If you make this grid three-dimensional, you will have. No, the relationship. No, so here it's part of the question. So basically, here yeah. How do we come up with these bijections? Okay, so those bijections are not so intuitive. Okay, and so you will need to do hard work to get them, to think about them, and you may fail several times. So basically, here we are using end product. So there were mathematicians thinking about these problems and coming up with those bijections. So there is no like straightforward algorithm like to obtain bijections. Okay, so it is not easy. So in this problem, we are taking this for granted. So some smart guy came up with this idea, and what we are trying to do now is to ask ourselves, we are trying just to verify. Okay, so is this really a bijection? If I give you, so one direction of the verification is very straightforward. Given x and y, it is very straightforward to compute S, but the other one is not that straightforward, but we did it, and hence we do have a bijection. But again, it's not, so this is in the problem set in homework 1. Basically, I gave you the bijection. So don't worry about, I'm not leaving you to basically think about how to generalize this. I gave you the formula, and you just need to do an exercise that is very close to what we have done here, and see if I give you, now if you have S, now can you obtain the triple X, Y, and Z? Okay, so of course it will be something very related to what we have on this slide here. Okay. Now some rules to keep in mind. Okay, so if A is a subset of B, then the cardinality of A is less than or equal to the cardinality of B. So it cannot be the case that A is a subset of B and the cardinality of A is larger. But we now know that A can be a strict subset of B, and yet the cardinality of A being equal to B. So this is something that we have seen now. But there is, it is not possible to have a subset with a strictly larger cardinality. Okay, so this is the first point. The second point, which is very useful, is that if you have basically countably infinite sets, so those are sets with cardinality Aleph Naught. So those are things like, the set of natural numbers, integers, rational numbers, and so on. So basically, if you have a finite or countably infinite union of those sets, you still get a set with a cardinality that is Aleph Naught. Okay, so we'll take this for granted. Of course, it has a proof. We'll take it for granted, and let me see. Okay, so let me like give you how this can be useful. Okay, so let's take the set of real numbers. Okay, the set of real numbers, and real numbers basically are rational numbers and irrational numbers. Okay, so numbers that can be written as the ratio of two integers, and the integer in the denominator should not be 0. And those are basically the irrational numbers, and those irrational numbers are the numbers that cannot be expressed as a ratio or a fraction. Now, what is the cardinality of irrational numbers? Okay, so we can do it by contradiction. So if you assume that irrational numbers basically are countably infinite, so if the cardinality of the irrational numbers is Aleph Naught, so according to this property here, the rational numbers, they have a cardinality Aleph Naught. The irrational numbers, under our assumption, they have a cardinality Aleph Naught. So according to this property, their union should have a cardinality Aleph Naught. But this is not true, because we know that the cardinality of the real numbers is C, and C is strictly greater than Aleph Naught. Okay, I didn't show this, you know, in the lecture, but you can just take it for granted. You know, I just said one thing, that the set of real numbers can be thought of as the power set of the natural numbers. Okay, so C is strictly greater than Aleph Naught. Okay, so it cannot, so this assumption is wrong. It cannot be true. Okay, it cannot be true again, because if it's true, and we can use this property to say, okay, if the irrational numbers are also countably infinite, then their union with the rational numbers should be a countably infinite set, a set with cardinality Aleph Naught. But we know that the union has a cardinality that is C, which is strictly greater than Aleph Naught. So this assumption is wrong. And because the irrational numbers are a subset of the real numbers, so definitely they cannot have a larger cardinality. Okay, so the cardinality of the irrational numbers is C. Okay, the cardinality of irrational numbers is C. Okay, so this is C, small c. Okay, so there are so many irrational numbers, okay, relative to the rational numbers, and this may be like a surprising result. And we will talk, you know, basically rational numbers and irrational numbers both are dense on the real axis. Okay, so I will just say this here. You know, so this is something aside from the business of set cardinality. Rational numbers and irrational numbers are dense, meaning that basically this is the real axis. If you take any open interval on the real axis, no matter how small, you are guaranteed in this open interval to find a rational number and an irrational number. Okay, so you can always find a rational number. In fact, there are infinity irrational and rational numbers in any open interval on the real axis. Okay, so this is the meaning that the set of rational numbers is dense and the set of irrational numbers is dense. Okay, so dense here means that, again, they are everywhere. They are everywhere. Take any open interval, you know, of any size of your choice, and there are always rational and irrational numbers living there. Okay, arithmetic of cardinal numbers. Okay, so cardinal numbers, again, our heroes, you know, because this course is not like about, you know, set theory and so on, so we will just focus on Aleph Naught and C. So the arithmetic of cardinal numbers is somehow surprising, and there are things that you see in front of you right now that should not be extended to, you know, to finite numbers. Okay, so there are here, so Aleph Naught, if you add a finite number to it, a finite natural number to it, or if you multiply Aleph Naught by some finite natural number, or if you take Aleph Naught and raise it to a finite natural number, in all cases you still get Aleph Naught. So you may wonder, what is the meaning of this thing? The meaning of this thing is, for example, I mean, what is the meaning of these two guys? Okay, so this means that basically if you have the one-dimensional grid of natural numbers, 1, 2, 3, 4, 5, 6, if you take r equal to 3, then if you have a three-dimensional grid of natural numbers, okay, then basically the cardinality of this grid of of this three-dimensional grid of natural numbers is still equal to Aleph Naught. Okay, so we proved something like this for non-negative integers. Okay, so this is the meaning. Okay, so the meaning is that Aleph Naught to the r is equal to Aleph Naught. Again, it means that basically a three-dimensional grid of natural numbers, it has the same number of elements as a grid, as a one-dimensional grid of natural numbers. And again, if you feel that this is, you know, nonsensical, no, it is not. I mean, we proved something like this for non-negative integers in a previous slide. Okay. Now, what about C? We can write C as 2 to the power Aleph Naught. Okay, I didn't go into details, but again, this is inspired by the fact that real numbers can be thought of as the power set of natural numbers. And in fact, rather than 2, we can have any natural number, and this will be okay. Now, if you take C and add to it any finite natural number, or if you add Aleph node, or if you multiply by a natural number or Aleph node, or if you raise to the to a natural number, or basically to Aleph node, you get C. Okay, so so I'm claiming here that C to the Aleph node is actually C, and one way of seeing this is that C to the Aleph node is, so C itself is 2 to the Aleph node like this. Okay, so what is 2 to the, so if you have something raised to some power and then everything is raised to another power, then you what do? You multiply the powers. So this is 2 to the Aleph node times Aleph node, and guess what? If you multiply Aleph node by itself a finite number of times, you get Aleph node, and so this is equal to C. Okay, weird, true, but true. Okay, so those cardinal numbers, they have certain rules, and of course, I mean, we'll not go into basically rigorous derivations of these rules. We will just we'll just use them. And let's do another one here, which is nice. What is Aleph node to the power Aleph node? Okay, so Aleph node, definitely, so this is basically the cardinality of something like the set of natural numbers. It is definitely greater than 2, right? Aleph node is definitely greater than the finite number 2. So Aleph node to the power Aleph node is greater than or equal to 2 to the power Aleph node, which is C. Okay, so we know that this quantity is greater than or equal to C. But also we know that Aleph node is strictly less than C. Okay, by this argument, that basically, real numbers are uncountably infinite and they have a strictly larger cardinality than the natural numbers. But C to the power Aleph node is equal to C. So this quantity here is less than or equal to C. So if something is greater than or equal to C, and something is less than or equal to C, then this thing is equal to C. So Aleph node to the Aleph node is equal to C. And again, just basically jump into homework 1 and you will see basically things like this in action. Okay. Sets of measure 0. Okay. Now, again, this is like from measure theory. Again, if as I said at the beginning of this lecture, if we want like to do things like rigorously in signal processing, we should like do Lebesgue integrals. But it turns out that it's enough to know about sets of measure 0. So the Lebesgue measure is a generalization of the idea of length in 1 dimension, area in 2 dimensions, and volume in 3 dimensions, and so on. We will focus here on 1 dimension. So the Lebesgue measure of intervals, is basically the length of interval as we know it. Okay, so if I give you an interval, regardless of whether it is open or closed, or semi, half open, half closed, and so on, basically the length of the interval, so you take A and B, and basically the measure is the length in 1 dimension, and it's simply B minus A. So that's the measure associated with intervals. Now, the Lebesgue measure, again, it's a generalization of the idea of a length. It is sub-additive. Sub-additive, which tells you that now if you have sets, and you have, what is the measure of the union of the sets? Basically, this should always be less than or equal to the sum of the measures of each set. So this is a generalization of the idea that if I give you 2 intervals, okay, so this is 1 interval, okay, and let me give you another interval. So let's say we have another interval, which is this one. So basically, the length or the measure of the union, so the union is basically the interval going from here to there, the length of the union is always less than or equal to the sum of the length. Okay, so again, this is the idea written in an abstract way. Okay, now if the sets are disjoint, so if we are talking about intervals that are disjoint, and I tell you what is the overall length of these sets or these intervals, then you just sum the length. Okay, so basically for measure, the measure is additive. If you have the union of sets that are disjoint, then the measure is equal to the sum. Okay, so again, there is something called Lebesgue measure. In one dimension, you can think of Lebesgue measure as the length of a set. But this set can be complicated, right? The sets for which you can very intuitively think about of a length are basically the intervals. For intervals, the Lebesgue measure is simply, an interval from A to B. The measure or the length is simply B minus A. The measure function, okay, is basically it is if you apply the measure to a union of sets, then you get something that is less than or equal to the sum of the measures. And if the sets are disjoint, then you get the sum. So basically this inequality will become an equality. So there are so many sets that are of measure 0. And so sets of measure 0 basically are defined as follows. A set is of measure 0, okay, if we can cover it by another set, and we can make the measure or the length of the covering set as small as we wish. Okay, so a set L of measure is said to be a set of measure 0 if there is another set C such that L is a subset of C. So, sometimes we say that C covers L. So if C covers L and we can make C arbitrarily small in measure, if we can make the length of C as small as we wish, then we say that set L is a set of measure 0. So let's study. So this is our first example of a set of measure 0. Basically, it is a set that is composed of m different real numbers, x1, x2, up to xm. So I claim that a set with a finite number of real numbers, this set is an example of a set of measure 0. Why is this the case? Okay, so here is xj, for example. Okay, so this is xj. This is one element in this set. I can cover xj by defining an interval around xj that goes from xj minus epsilon over 2m to xj plus epsilon over 2m, where epsilon is some positive number, right? So again, you can choose a positive number epsilon. If epsilon is a positive number, positive real number, then if you divide it by 2m, and m is the number of points that you have in this set, you still get a positive number. And so you define an interval going from the point xj minus epsilon over 2m to xj plus epsilon over 2m. So now xj is definitely in xj minus epsilon over 2m to xj plus epsilon over 2m. Okay? So L, which is this set of m different real numbers, L is a subset of this union. So this is a union of intervals Okay, basically each interval in this union is an interval that is centered about xj, and it goes, basically from xj minus epsilon over 2m to xj plus epsilon over 2m, where epsilon is some arbitrary positive real number. Okay, so what is the measure? What is the measure of C? What is the measure of this cover? The set that includes L, the set that covers L, the set that contains L. Well, what is the measure? What is the measure of this thing? Well, if you want to find quote unquote the length, then you may say, well, I mean, we need to know whether those intervals are overlapping or not overlapping, are they disjoint or not disjoint, and so on. But we do not need to worry about this, because we can, rather than measuring the length of C, we can just upper bound it by using subadditivity, which tells you, the measure of the union is strictly less than the sum of measures. So this summation here is not, it is the measure of C if it happens that the intervals are disjoint. If they are not disjoint, then this is an upper bound on the measure of C. Okay, so what is the measure of any of those intervals? So the measure of an interval, again, is just the length. And what is the length? You take this guy minus this guy. Okay? And so, in other words, you just compute the distance between these 2 points. And what is the distance between these 2 points? It is epsilon over 2m minus epsilon over 2m. Okay? And so, basically, it is epsilon over m. So the length of any of those intervals from here to there is epsilon over m. And so C, it has a measure that is upper bounded by the sum of epsilon over m. Epsilon is a constant, some positive constant. You can take it outside, and m is also a constant, right? So basically you have epsilon over m summation j from 1 to m, and you are summing 1. So this is 1 plus 1 plus 1 plus 1 m times. So this summation is equal to m. So we have epsilon over m times m, and this is epsilon. So basically set L, which is a set that is composed of m real numbers. So this set can be covered by set C, and the measure of set C can be upper bounded by epsilon. But epsilon is any arbitrary positive number. You can choose epsilon to be 10 to the minus 100 or 10 to the minus trillion. You can make epsilon as small as you wish. So L is a set of measure 0 because L can be contained, can be covered by a set that can be made arbitrarily small in measure. So all sets that contain a finite number of points, all those sets are sets of measure 0. But what if L is a countably infinite set? So we have numbers. I mean, these numbers, what if L is equal to 1, 2, 3, 4, 5, 6, and so on? What if L is the set of rational numbers? It turns out that also, if your set is countably infinite, then it is also a set of measure 0. And the trick here is that now you take xj, an element from this set. Now there is an infinity of those guys. But you take some xj and you include it, you cover it with an interval. You pick a positive epsilon And your interval now will go from xj minus epsilon over 2 to the j plus 1 to xj plus epsilon over 2 to the j plus 1. So it means that for the first number x1, you cover it by an interval from x1 minus epsilon over 4 to x1 plus epsilon over 4. But when somewhere here there is x2, you cover x2 by an interval x1 minus epsilon over 8 to x2 minus epsilon over 8 to x2 plus epsilon over 8. And you go to x3 and you cover it by the interval from x3 minus epsilon over 16 to x3 plus epsilon over 16, and so on and so forth. So basically the trick here is that you take the first point and you cover it with an interval of length epsilon over 2. Then you cover the second point, x2, by an interval with half the length. And then x3, you half the length again, and so on and so forth. All those intervals have positive length. For any j, the length of any of those intervals is a positive number. The number is getting ridiculously small, but it is still a positive number. Now, what is the measure of the union of those intervals? Again, rather than worrying about those intervals because you may have overlaps, you can simply say that the measure is upper bounded by the sum of measures. Now, the intervals, they do not have the same length as in the first case. They have a length that decrease. So basically the length of the jth interval that is covering xj is epsilon over 2 to the power j. Now, you have a geometric series, and it is a converging geometric series because its ratio is 1/2, which is strictly less than 1. And so basically this summation here, which is an infinite sum, it does converge, and if you evaluate it using the formula for the geometric series, you will get epsilon as an upper bound on the measure of C. So L is contained by C, and the measure of C is upper bounded by epsilon, and epsilon can be chosen to be as small as we wish. We can make it ridiculously small. And so L, which is a set of points, a countably infinite set of points, this set here, which has the cardinality of the natural numbers, and so we can say x1, x2, and so on. Because it's countably infinite, we can index this set with the natural numbers. That's the reason we here say x1, x2, and so on. This set is a set of measure 0 by our definition. It can be covered by this set C, and the length or measure of C can be made arbitrarily small. So basically L is a set of measure 0. So any countably infinite subset of the real numbers is a set of measure 0. So this is applicable to the rational numbers. So the rational numbers are dense. They are everywhere on the real axis. However, their length is equal to 0. And this will have consequences that we will investigate at the beginning of the next lecture. Okay, so the set of rational numbers, surprisingly, it has a measure of 0. Its length, quote unquote, its length, its Lebesgue measure, which is a generalization of the idea of length, is exactly equal to 0.